Hello, everyone. We're going to do logistics equations today. So, honestly, a lot of it is similar to what we did in pre-calculus. We just need to define the logistics growth by a differential equation. So, what we know is that a logistics curve looks like, at first, it looks like an exponential curve, and then I need to connect my. Okay, and then it increases quickly, and this is the fastest point. The point of inflection is the fastest point that the graph is increasing, and then it still increases. It just increases at a slower rate. Okay, so it slows down. Um, what we have is that the the population or the logistics curve is modeled by m is over 1 plus c e to the negative kt, where m is the carrying capacity, k is the relative growth rate, and c is the it helps us find our initial value. Okay, remember that c is not the initial value. To find c, you have to plug in 0 for t and figure out what 1 over m over 1 plus c is, and that will give you your initial value. Okay. The differential equation that models the growth, so the growth of the curve, is this here. dp over dt is equal to kp times 1 minus p over m. And I honestly just memorized these equations and that they go together because I do not want to do the proof that maps one to the other every single time I need to solve a logistics equation. It's possible, it just takes a long time. Okay, so another important part is that the curve is growing the fastest when at half the carrying capacity or when the population is m over 2. So carrying capacity over 2. All right, first example. A state game commission releases 40 elk into the game refugee. After 5 years, the elk population is 104. The commission believes that the environment can support no more than 4,000 elk. The growth rate of the elk population, P, is dP over dt is equal to kp times 1 minus p over 4,000 when P is between 40 to 4,000, where T is the number of years. Okay, let's break that down. I got 40 elk were released, so that would be equal to P of 0. And after 5 years, we have 104 elk, so P of 5 is equal to 104 elk. Okay, I have a carrying capacity of 4,000 since we can't have more than 4,000 elk in the refugee. Okay, refuge. Game refuge? I'm just like, okay, anyway. Write a model for the elk population in terms of T. So we already have our rate of change, but we don't know what the K value is. From this equation, the rate of change equation, I can see that M is equal to 4,000. So I am going to start by being like P of T is equal to my carrying capacity over 1 plus C e to the negative KT. And I need to start filling things in. So I got 4,000 over 1 plus C e to the negative KT. And then I know P of 0 is equal to 40 elk. So I'm going to go ahead and do that so I can solve for C. Okay. So I get M over, 4,000 over 1 plus C e to the negative K times 0. And anything to the 0 power is 1. So now I have 40 times 1 plus C is equal to 4,000. Divide by 40. And I get 1 plus C is equal to 100. So I can see C is equal to 99. So now I have P of T is equal to 4,000 over 1 plus 99 e to the negative kt. So next step is to solve for k, and I'm going to use my second point, 5 comma 140. So I end up with P of 5 is equal to 140, which is equal to 4,000 over 1 plus 99 e to the negative k times 5. Okay, I'm going to multiply both sides by 1 plus 99 e to the negative 5k times 140 is equal to 4,000. Divide by 140 gives me 1 plus 99 e to the negative 5k is equal to 4,000 over 140. Subtract 1. Okay. Is 99 e to the negative 5k is equal to 4,000 over 140 minus 1. I honestly put that in my calculator and I got 487 over 1,200, nope, 1,000, 300, over 13. Yeah, over 13. Okay, then I divide by 99. Should have used two colors in my notes. All right, e to the negative 5k is equal to, and then multiply by the reciprocal, so 487 over 1,287. Change forms. ln of 487 over 1,287 is equal to negative 5k. Whew. All right, now we're almost there. We just got k is equal to the ln of 487 over 1,287 divided by negative 5, which is equal to 0.194, and I am going to stow this as A. Okay, we definitely need that. And then so now I can fill out my model. P of T is equal to 4,000 over 1 plus 99 e to the negative, because remember K is, you have to plug in the negative value, 0.194, which I remember is A, to the T value, to the T. I said that weird. All right. Okay, so that's part A. Part B is use your model to estimate the ELK after 15 years. So we're going to do P of 15, since that's years. Okay, over 1 plus 99 e to the negative 0.194 times 15 is about equal to 628.538 ELK, or 629 ELK. Okay. All right, so the limit as our model approaches, t approaches infinity. So this is the limit as t approaches infinity of P of t is basically the carrying capacity. It's m. We're getting close to this topped out number, remember, because our curve looks like this, where we get closer and closer to an asymptote. Okay, so 4,000 ELK. Guess I could have used the highlighter. Okay, so when is the population increasing the fastest? And remember, it is increasing the fastest at the inflection point of our curve, or half of the population. So when P of T is equal to m over 2, our carrying capacity is 4,000. Divide that by 2 to give us 2,000. So that's the population. Now we need to plug it in to find the coordinating time. So I get 2,000 is equal to 4,000 over 1 plus 99 e to the negative 0.194 t. Okay, multiply both sides. So I get 2,000 times 1 plus 99 e to the 0.194 t is equal to 4,000 divided by 2,000. So see I get 2 is equal to 1 plus 99 e to the negative 0.194t. We're going to subtract 1, which gives me 99 e to the negative 0.194t is equal to 1. Divide by 99. So I get e to the negative 0.194 times t is equal to 1 over 99. Change our form to isolate our exponent. So I have the ln of 1 over 99 is equal to negative 0.194 times t. Divide by negative 0.194. So I get t is equal to 23.64 years. Ta-da! Make this better. All right, so this time I'm going to give you an equation and you just need to pick out the correct pieces. So the equation, oh, I guess I gave you the differential equation this time. This time I'm giving you the population equation, so a logistics equation. I recognize this as a logistics equation. So I am going to pick out the value of k. You can see the value of k is equal to negative, oh no, is equal to 0.2 because the negative is part of the equation, so the k value is opposite. The carrying capacity is the top value, so I have m is equal to 5,000, okay? The initial population, so p of 0, is equal to 5,000 over 1 plus 39, and then e to the 0, so that's 1. So 5,000 over 40, which gives me 125, okay? And then we're going to determine when the population will reach 50%. So this time we can totally use our calculator to do this. We can totally do it by hand. So when the population is 25%, it would be 2,500. So I would set this up as 2,500 is equal to 5,000 over 1 plus 39e to the negative 0.2 times t. So I went ahead and did that in my calculator. I plugged in y1 as 2,500 and y2 as our logistics curve. And then I'm going to go ahead and graph it. I changed my window to negative 10 to 5,000 because that's my carrying capacity. And then the x's I just guessed. So I did negative 10 to 50 so that I could see the curve a little bit better. And then I regraphed my x just in case. I think I had to change my window twice to get it to work, okay? Then I look at the intersection. So I'm going to go to second calc, 5 for intersect. And then we do the first curve, enter, moves to the second curve, go to close to the intersection, guess, and I get a value when y is equal to 2,500, I get a value of 18.3178. So when t is equal to 18.317 truncated or 18.318 rounded, okay? Either of those will work. Okay, so write a logistics equation that has differential equation that has the solution of P of t. So what I need to do is write the rate equation. So dp over dt is equal to, and it's k times p times 1 minus p over your carrying capacity. So that is going to equal 0.2 times p is the input times 1 minus p over 5,000. And then with our initial condition of p of 0 is equal to 125. All right. Next up is we have a population of wild horses that is represented by the logistics differential equation. dP over dt is equal to 0.08p minus 0.00004p squared, where t is measured in years. Now, this one doesn't quite look like the logistics function that we know, so I'm going to change its form. I'm first going to GCF out a p, so I get 0. Actually, you know, I want it to look like k times p times 1 minus p over m. So I'm actually going to GCF out a 0.0, oops, 0.0000124 p. So I get, when I divide 0.08 by 0.000004, I get 2,000 minus p. So we're getting close. We just need a 1 with the 2,000. So I'm also going to GCF out a 2,000. So dP over dt is equal to, and when I take out the 2,000, I'm actually multiplying this 0.00004. So I get 0.08 times 1 minus p over 2,000, since I'm also taking out a 2,000 from my second term. Now we look like a logistics function. So the k value is equal to 0.08, and the carrying capacity is equal to 2,000, because we're matching our form now. All right, next up, it says the initial population is 10 horses, so find the formula for P of the population in terms of T. So we want P of 0 is equal to 10 is our initial condition. So I have P of T is equal to, let's see, our carrying capacity is 2,000 over 1 plus C e to the negative K T. But we actually know what K is, which is negative 0.08 T. So now we just need to solve for C. So I'm going to go ahead and do that on the side. So P of 0 is equal to 2,000 over 1 plus C e to the 0. Okay. So, and that is equal to 10. Multiply both sides by C1 plus C. So 10 times 1 plus C is equal to 2,000 divided by 10. So 200 is equal to 1 plus C. So C is equal to 199. So now we can go ahead and substitute in the C value. So 2,000 over 1 plus 199 e to the negative 0.08 times T. Okay, and then how long will it take for the horses to reach 350? So we have 350 is equal to 2,000 over 1 plus 199 e to the negative 0.08 t. Okay, you can solve this by hand, but I'm just going to use the calculator again. I looked for the intersection, and I got t is equal to 46.783, or t is equal to 46.784 years truncated. Oh, the first one's truncated, the second one is rounded. And that is it. Okay,